Lecture 4, Part 1. In this lesson, the method of Castiglione theorem is used to calculate deflection and rotation under different load conditions on different boundary conditions. We will see in this method that we will use load B at the point where we want to find the deflection and use a partial derivatives in the equation and compared to the virtual work method, which we use unit load at the point where we need to find the deflection and integration in the equation. Example: determine the vertical displacement at the end B of the cantilever beam, which is fixed at support A as shown in figure below. The modulus of elasticity E is equal to 200 times 10 to the power 6 kilonewton per square meter, and the moment of inertia I is equal to 500 times 10 to the power 6 millimeter to the power 4 of the entire beam. The explanation of the method will be in steps to make the method easier. 1. Apply the equation of Castiglione theorem to determine the desired displacement delta and rotation theta as below. Delta is equal to the integration of m, which is internal moment in the beam or frame caused by both the force B and the real loads on the beam, times dm over dB, which is the partial derivatives of m with respect to the force B. The force B is external force applied to the beam or frame in the direction of delta. EI flexural rigidity we will take as constant. Then the equation of rotation or slope as below. Theta is equal to the integration from L to 0 m times dm over dm dash. M dash is the moment applied to the beam where we want to find the slope at the point. Step 2. A vertical force B is placed on the beam at the point P as shown below. After we apply force P at the point B, we will take section X from the load B as shown in the figure. Then we will take moment at point O, sigma m at O equal to 0. The positive sign is counterclockwise. So the equation will be minus m 12x times x over 2, the distance for the uniform load to the point O, minus b times x equal to 0. So m will be minus x square minus px. The partial derivatives for m with respect to bp equal to minus x. Setting b is equal to 0 because this was imposed by this method, which is in fact does not exist. Then we find the deflection by applying the equation of Castiglione method, m times partial derivatives m with respect to p times dx over ai. Then the deflection will be 0.15 meter, which equal to 150 millimeter. The following example will show how we will find the slope at point by using Castiglione theorem. Example: determine the slope at the point P of the cantilever beam, which is fixed at support C as shown in figure below. The modulus of elasticity is equal to 200 times 10 to the power 6 kilonewton per square meter, and the moment of inertia is equal to 600 times 10 to the power 6 millimeter to the power 4 for the entire beam. Two segment will be take at this beam. First, the section x1 from the load 3 kilonewton to the point O. Then the section x2 where the moment will be changed from the point B to the point O as below. For the first section, external moment m dash is placed on the beam at the point where we want to find the slope. We take then moment at the point O, m1 plus 3 and the distance x1 to the point O, so m1 will be minus 3x1. Then the partial derivatives m1 to the dm dash is equal to 0. For x2, we will take moment at point O. Then this will be m2 minus m dash plus 3. The distance for the force 3, 5 plus x2 is equal to 0. So m2 will be m dash minus 3 times f plus x2. Now we setting m dash is equal to 0 because this was imposed by the method which is in fact does not exist. Then we will take the partial derivatives for m2 with respect to m dash, and that will be equal to 1. After that, we will apply the equation of Castiglione to the beam, and will be two parts for x1 and for x2 as shown in this below equations. The theta b, the slope at point B, then will be equal minus 0.000938 radius. So theta b is opposite to the direction m dash because the result is in the minus. Thank you.